nice to see that you're attracted by this subject, and how nice to see that you are here. I will briefly introduce myself. I'm a little bit nervous. I hope you will not mind. I will briefly introduce myself, tell something about the quantum computer. Yes, why we should monitor the quantum computer developments. What are the known complications, the known unknowns, the comforting certainties, and last but not least, I will share with you the abstracted low-regret moves. Okay, I'm active in the payment industry since the early 2001, August. I was for 12 years responsible for the certification program of Dutch payment terminals. Today, I'm cybersecurity analyst for the Dutch Payment Association, and I'm chairman of the Dutch Interbank Security Working Group, member of the curriculum committee of the course running course Applied Cryptography, and chairman of the ECPA was already expressed, and a member of the PCI PTS working group. Okay, this is a picture of a quantum computer. This quantum computer uses quantum mechanics to process information. It uses qubits in superposition, and it is very sensitive for environmental influences. We see a nice chandelier, and at the bottom there's the quantum processor. It likes to operate in a chilly environment of 30 millikelvin or minus 270 degrees Celsius or minus 460 Fahrenheit. So this nice chandelier will be hidden in a refrigerator and not on your desk anytime soon. To be able to understand something about quantum computers, you should know something about quantum mechanics, superposition. It's very hard to understand. Particles can have both states at the same time. Let's give me an example which comes close. If we toss a coin, it's not determined head or tail as long as the coin is in the air. If I catch the coin, then it's determined whether it's head or tail. For quantum mechanics, it is really two states at the same time. If we do an observation, then it is determined whether it is head or tail or what kind of state it is. Another important aspect is interference. Particles can interfere like waves in the pool. It can add or it can cancel each other. And the last concept is entanglement. Particles can be entangled, coupled, and become one system. Even if the particles are from a large distance separated, they still operate as one system. If you do an observation at one side, both are directly collapsing to the same state. Okay, our current computers work with bits, and the quantum computer uses qubits in superposition. Every time you add a qubit, the power of the quantum computer doubles. So that ramps up very rapidly. But a quantum computer, when it becomes available, it really will be a disruptor. A quantum computer can simulate the properties and behavior of molecules. For making fertilizer, nitrogen fixation is a very important step. But as we humans do it, it consumes 2% of the total energy consumption. But Mother Nature is doing it far more efficiently. Bacteria are able to do the same process in the cell membrane at room temperature and at atmospheric pressure. So we can learn from Mother Nature. We would like to simulate this, but we are not able to run it on a supercomputer. We're running out of memory and running out of computational power. But Ryder and others have done research, and it appeared that a quantum computer is able to run this simulation, and then we can learn and understand how Mother Nature is doing this. So that will be a very important step forward, and we will save a lot of energy. So this will not stay unnoticed. But why should we monitor the developments of the quantum computer? Security brings us together, and if we want to secure data or payment transactions, we often use encryption. And encryption is incorporated in many business processes. Symmetrical encryption is one part, asymmetrical encryption is the other part. Symmetric encryption, I like. It's really fast, but has a big disadvantage. It has only one key. So every time if you want to exchange a key, it's a bit tricky. And for every communication channel, you need another key. So it becomes often a key management challenge. On the other hand, we have asymmetrical encryption. It's very slow, but it offers us flexibility. And it gives us the opportunity to monitor the integrity of software. It opens up the opportunity to organize non-repudiation. And it gives us the opportunity to exchange keys in an open network. So many of our business processes use both symmetric encryption and asymmetrical encryption. And in general, we can say encryption raises a barrier for using a hard problem. But what a hard problem is for current computers is not always a hard problem for a quantum computer. There are two algorithms known which can weaken our encryption importantly. The first one is from Grover. The Grover algorithm weakens our symmetrical encryption. And we can act on that, double the key length, and we are fine. However, if we're running DES, we're not having the opportunity to double the key. So please migrate to AES. If it concerns the collision risk, Grover doesn't have a very huge impact. So if you're using SHA-2 and more recent, you're fine. But then, the Shor algorithm really breaks the asymmetrical ciphers we are using today. Let's give me an example. RSA has a hard problem. Factorization is a hard problem. If you want to find the original primes from a large number, in example 2048 bits, you can use the best algorithm known, GNFS, and run it on a supercomputer. It will roughly take 10 to the power 34 steps to find the answer. If I run it on a supercomputer, which operates at 1 trillion operations a second, it roughly takes 317 trillion years to get the answer. In that case, it's well protected. However, if we give the same challenge to the Shor algorithm, it only needs 10 to the power 7 steps. If we run that on a quantum computer, which operates at 1 billion operations a second, then the answer becomes available in 10 seconds. In that case, we can conclude RSA is broken. We need a quantum computer which has 4,099 logical qubits. The greatest or the biggest quantum computer I'm aware of is the one from IBM, the Eagle, which has 127 noisy qubits. To be able to construct a logical qubit, I roughly need 1,000 till 10,000 from these noisy qubits to be able to construct one logical qubit. So that gives us some time. Okay. If you're managing state secrets, perhaps you have already a small challenge. If you're communicating over open networks like internet, your adversary can intercept all the communication, wait patiently till the quantum computer becomes available, and decrypt your secrets and reveal it. But we do process transactions, and the biggest advantage of the transactions, once they are processed, they become irrefutable. So here the theorem of Michele-Lamoska comes at hand. X stands for the security shelf life. Your algorithm in combination with your key, how long can you use it securely? Y stands for the migration time. How long will it take to migrate from your quantum vulnerable algorithm to a quantum resistant algorithm? If the quantum computer becomes available before you've finished your migration, you're in trouble. That is well understood by NIST. We need alternative algorithms which can replace these quantum vulnerable algorithms. And they have organized a contest to find new post-quantum crypto ciphers which can run on the classical computer architecture. The contest is still running, and we expect a finalist and new standards between now and 2024. But how much time is given? Nobody knows. Michele Mosca stated in 2015 he believed the chance is 1 on 7 that a quantum computer is able to break an RSA key of 2048-bit in 2026. And he believes that the chance is 50% that a quantum computer is able to do so in 2031. Recently, he re-performed this and asked colleagues in the field, experts, and they said, oh, the chance is 50% that we are able to do so in 2036, 15 years from now. Okay. This statement of Michele Mosca perfectly expresses the likelihood increases over time, but for now we can assume 15 years. But we always overestimate what is happening in the two coming years and underestimate what is coming in the next 10 years. So don't sit on your hands. What are the known complications? Let's give an example near to us. The service life of a smart card platform can range from 8 to 17 years. You select the card platform, bring it for certification, and if it meets all the requirements, you get an approval for 3 years. The card is issued for 5 years, so that makes 8. If this card platform still meets all the requirements, you can do a recertification, and you can do that 4 times, making 12. And the last card is again issued for a service life of 5 years, making 17. At the other hand, we have the point-of-sale and ATM machine. They have to have the same crypto cipher, and their service life ranges from 5 till 20 years. The average point-of-sale terminal in the Netherlands serves for roughly 7 years, and the ATM machine often longer. There are examples available where ATM served for 25 years. And as said before, we need a shared encryption cipher, otherwise we cannot construct a transaction. And the best way to introduce a new encryption cipher is doing it by the regular replacement cycle. Of course, you can speed things up, but it will be more expensive. And replacing a cipher is not that easy, especially if you want to replace it by a PQC algorithm, because that are not drop-in replacements. For optimal use, you have to redesign your protocol. And the standards are still lacking for a rollout of PQC standards, so work has to be done. At the other hand, there are also some converting certainties. Symmetrical encryption, AES, if you're using 128 or stronger, you're fine. If you're using hash algorithms 2 and more recent, again, we're fine. Also functions and algorithms based on the aforementioned algorithms still are fine. MAC algorithms, key generation and key derivation, they're all fine. Oh, and also the old concepts from the old days where we still used only symmetrical encryption, predating the asymmetrical cryptography, also remain secure. So our security officers with key letters, that's a good protocol. Oh, and we have a canary. There are less demanding applications that will be known, like this example with this fertilizer, nitrogen fixation. And only later the quantum computer becomes strong enough to break our encryption. The unknown, yeah, still we do not know when the quantum computer becomes available. The field of quantum computing and PQC is still highly in flux, and we're missing an inventory of the business processes which make use of encryption. Okay. Based on all this information, we drew up 7 low-regret moves. First, a no-brainer, monitor the developments of a quantum computer. Draw up a FAQ. You can expect very tricky questions from media. Better have them well prepared. Secondly, make an inventory of all the business processes. which encryption algorithm is used, which key length is used, and what is the service life. If it is a quantum vulnerable encryption, explore what is the opportunity, what is a good alternative, what meets your business needs, and explore what is the migration timeline. Based on all these timelines, you get a good indication where to start. Okay, ask the international organizations like PCI to draw attention for this topic, because the international card payment infrastructure doesn't stop at your national border. So some international coordination is well appreciated, and also look in your supply chain. For symmetrical encryption, I've already said, migrate to IES, use SHA-2 and the secure derivation schemes. And for card payment infrastructure, develop a fallback. That needs some explanation. As already said, point of sale and ATM processed in the past all information using only symmetrical ciphers. We learned IES and SHA-2 are fine. We can use them as building blocks for MAC authentication, key generation, and key derivation. So that gives us the opportunity to construct and process secure transactions. Of course, we can also use promising PQC candidates for key exchange, but these are the important ingredients. On the other hand, we would like to have a flexible migration, secure software update, but secure remote updates must be supported by your operating system, meaning that your operating system should use quantum-resistant encryption ciphers. On its turn, an operating system is loaded by a bootloader. So the bootloader itself should also use quantum-resistant encryption ciphers. And then we turn in, to guarantee the integrity of the bootloader and the OS, you need these quantum-resistant ciphers. But then we run into the other challenge, implementing an encryption cipher in hardware. Paul Kocher learned us at the late 90s that if you're measuring physical characteristics during operation of a crypto system, you can learn something about the key by measuring time, power of electric radiation. For our current systems, we perfectly know how to defend against these side channel attacks. But for these new PQC standards, this information is still lagging. So we must get these experiences. And the obvious defenses use more computational power or memory, so better get started early. For our EMV smart card profile, develop a profile that does not rely on asymmetrical ciphers. Also, that needs some explanation. If you're using IES and if you're using and you're processing all the transactions online real time, you're not using asymmetrical ciphers for your security, so then it would be quantum proof. And last but not least, enforce to implement swiftly the latest TLS versions and get your hands dirty, gain experiences with PQC standards. And if you want to read it once more, we have written a small article. I hope that it will be a small summary. And I thank you so much for your attention.